I got a voice out there. Speaker. Right. If I can hear anything out there. Oops. I think I have something there. Yep. Okay. Hello, everyone. Let's get started. So, a few announcements. What? The quiz one. The solution has been posted and grading has been done, and you will see the final scores. If you have any problem with the scores and the grading, if you find some mistakes, just let me know. I can take a look at them again. But basically, I also regrade the multi-choice problems again. So you probably see like a 1 or 2 points bumped up because of the partial scores. And in terms of grading, I try to give you as much as possible. At least if you we have a formula in the top of the exam, but if you want to just pick some of the equation to trying to solve it, I try to grant some of the partial credits for that. So it's gonna be the same way for the exams too. So if you know how to solve it without knowing how to apply the equation, at least you need to try write out the equation and try to put the numbers in. Then I can just see whether you at least know what terms you're gonna working on for the final answer. So that's how the grading will be for this quarter too. What else? So average is like a, what? I wrote down like a 70, about like a 70 or a lower 70, I guess. It's not that bad. I can expect a little bit higher because of the multi-choice problem. I think it's not that obvious, but please take a look at the problems again. It's gonna come up in the other exams again, because the assumptions you need to apply when you drive the equation for the differential element method, those are really important. So please take them, take a look at on the solutions again. I'll post it on the canvas. So if you have any question, please let me know. Just one thing I want to mention for the stream function is the direction of the flow. I know it's not that obvious, right? It's not straightforward when you just look at the directions. Then if you can find the directions out of the numbers of the stream function, that's fine. You can just find a way. But if not, always you can just find the u and v, which is the velocity components of the these, what is it, x and y components of the velocity, right? Then you find the u and v is equals to -1. That means within the xy coordinate system, this means this direction, and v -1 is this direction. So by combining them all together, it's going to have an angle of a 45 degree. What happened there? Oh yeah, please do so. Yeah. So we can just find the direction of the flow in the third quadratic here. Okay, so that's another alternative way to find the direction of the flow. You probably get like a -1 deduction out of the flow direction. So I don't think it's a big of a deal, but so please take a look at the velocity here. Vorticity, stream function, yep, pretty much obvious. Just a few students have an issue with the constant term here. F function of x and function of y here. So basically you have same components -2xy cubed. So this term has to be constant, not the function of x or y anymore. Therefore, you can just treat this term as a constant, and that can be plugged into the psi here. That can make another psi, so which is just a stream function. So you can just end up having the one term expression here. And then multi-choice problem, you can just take it again. Take a look at those equations again, especially for one Navier-Stokes equation. I mentioned, I guess, more than twice during the lecture, nonlinearity has has been included within the convective acceleration, which is this portion. So other terms, do we have an equation here? Yes. Here, other term actually doesn't have it. So this is just a first order partial differential equation, first order partial differential equation, just a linear relationship, second order partial differential, second order. But here, convective term has a velocity with the partial derivative. So we have a combination of two here. So that's why it's really hard to solve this. And there's one way you can just eliminate this whole term, which is a Stokes flow, what we did in the lab 1. Okay, I think that's pretty much all, right? No initial condition for the steady state because everything is settled down in terms of time. And the assumptions here, convective acceleration, Newtonian incompressible. Okay. All right, any questions? I guess good. All right, let's take a look at the chapter 7 again. So,
Professor, I had a question.
Yes, sir. Go ahead.
Is it possible for you to show us which multiple choice questions we got wrong on the quiz? On Canvas?
Can't you see the answers? Your submission through the Canvas? I thought you can review them when you. Oh, can't you
Currently,
access
for me, it says correct answers are hidden.
No, I mean, didn't I post all the graded solutions on the Canvas? Can't you just download it? You probably have the PDF file that has a posted in the Canvas.
Okay.
Yeah, please take a look. Can anyone find it? Or has anyone,
I can't see my multiple choice answers either.
Okay, yeah. So I
think it's locked.
It's locked?
Oh yeah, it's hidden from your end.
Okay, I'll just take a look at the setting and just open it for you guys to take a look at your answers again. All right?
All right, thank you.
Yep. Okay, so anything else, if you have a question, please just send me a Teams message, especially, yeah, there's a typo in the lab handout in the second one. I didn't know I was gonna miss the squared in the one of the critical equation, which is a reference area of the sphere. So if you have any kind of problem, if you can't solve anything out of the equation, just let me know. I probably have typo inside. So, all right. So you have updated hands up, by the way. Please go ahead and download it. Now let's pick this up. So last week, it's like almost a week ago. It's hard to pick it up, but let's try. So we chose the repeating variables. Let's go here. For the example problem, so we picked just highlight. So we picked a repeating variable D and rho and B, just following some of the hints and the tricks we have here. Basically, out of the variables, we picked the D and V, obviously, because we have at least one M or L or T, then this is easy ones. But out of the rho and the mu, it's really hard to choose one of them out of here. Of course, we have a hint that just find the one kind of simpler and then pure quantity of the materials or the flow field, then it was density. But some can also insist, all right, what if I just choose mu? It's the wrong answer? No, actually, you can find the same dimensionless coefficient here by just choosing the mu then density here. So let's just do it today. Oh. It's not FLT method. Let me just go back my notes here. I think it's All right, just ignore it. I'm gonna just. So now repeating. Now we choose the. Let's just write down all. Oh, what's that? I think I'm just sharing now. Can you guys see my screen here?
Yeah, we can see it.
I think you gotta click the kind of screen or something there. I guess you have two screens at least, I guess. So we had a delta PL, it's a function of D rho mu V. Then now we choose the repeating variables D, V, and mu. Okay. So of course, all the same, the number of dimensionless coefficient is going, the pi term, let's just using pi term, is k minus r, which is just 2, right? You're going to see the two pi terms here. So first pi, we have this is the dependent variable that we are trying to figure out. Then we have repeating variables here, d mu v. Then you can just put the exponents here, a, b, c. So everything's same except for the mu now. So you can just write down this is unit, ml minus 2, t minus 2. Of course, d is l. Then we have m, l minus 1, t minus 1, b, l, t minus 1, c. So let's just use the different color here. So for, let me go first with m. We have a 1m here, then we have a b here, which is b0. So let's write down m, l, t, 0, 0. So we have a b equals minus 1. Then l, there's a lot of l's, so let's go for t first. We have a minus 2, and we have a minus b, and we have a here minus c. So b is a minus 1, so it's going to be plus 1, minus 1, 1. So c is also minus 1. Then lastly, we have L, which is minus 2, plus A, minus B, plus C equals 0. We have a B minus 1 is a 1, minus 1 is going to be 0, so A is basically 2. Yep. So it means we have a first pi is delta PL, then D with the A here, 2. Then mu and b, those are all with the minus 1. So this is our first pi term. It looks a little bit different, right? Let's just keep doing it. Second pi, we solved them. So one thing we didn't solve is a rho, and d mu v, a, b, c. And then this is m l minus 3, same l minus 1, t minus 1, l minus 1, t minus 1, and then exponents a, b, c. All 0. Okay. Oh, if you solve them, you find the pi 2 is going to be just simply rho vd over mu. Okay. What is this? this is Reynolds number, right? So for the D diameter. So we have one here, another set is here. But those are a little bit different from the one we have here. Of course, we had a Reynolds number, which is a reciprocal of the pi 2. That was what we can find from the pi 2. Then we set it as a pi 2 prime. Then pi 1 is now different. The first one is a dPLD. It was a square in our result. Now it's a rho v square. Then what we have here is the dPLD square, the rho v. So it is different. Are the right ones? Let me just check. So we are dealing with a dimensionless coefficient. So pi terms are dimensionless. So you can just take the roots or make it squared or divide by the another terms. Units are still, I'll say not zero. Well, there's no units anymore. So all numbers should have no units. It means you can just manipulate the pi terms one to another. So what I'm going to do is I'll just label it prime here, because we already set the pi 2 prime in the previous step. So if I just find the pi 1 prime over pi 2 prime, let's just multiply it, rho vd mu. So we can just find something else. D rho v square. Okay, what is it? Let's go back here. This is exactly the same form of the pi 1, right? So this is, let's see, pi 1. So this is how we can manipulate the pi terms. If you look at here, I just put the two graphs here. So first, this one was a pi 1. Just pi 1. And this one is a pi 2 prime, which is the 1 over pi 2. And this is just the pi 2 prime. Of course, same. This is pi 1 prime. Okay. So you can just find a pair of the unitless pi term here. First pair is going to be pi 1 and pi 2 prime, or pi 2. That's fine. You can just take the reciprocal here. But this is known dimensionless coefficients. That's why we use a Reynolds number. But if it's not known, you can just use a reciprocal of this form. That's fine. But once you just run the experiments, you can get the data, right? Then plot these types of data. But what if I chose the pi terms in this form? Yep, you will have a different answer, right? But the thing is, you can convert this whole graph divided by the Reynolds number, which is a second pi term, then it's going to be easily converted into the first form of the data. So this is not wrong. This is not incorrect way to solve it. Both of them are correct. So you can just choose either like rho or mu as a repeating variables. You'll see a little bit different form of the answer, but that also gives you the right answer. The problem is if you know the kind of common coefficients like Reynolds number, Froude number, Mach number, things like that, you can just convert into the, put that into the one of the x-axis, which is a known dimensionless coefficient. Just one thing I want to mention here is, of course, you can just manipulate the pi terms back and forth and divide by another one. That's what it says here. If we have like this example, we have 3 pi terms. Pi 1, pi 2, pi 3. Out of 3 pi terms, you can find new pi terms, which is, let's say, pi 2 prime by multiplying pi 2 with the to the a exponent and the pi 3 to the b. Then you can just find, let's say, have another new one. Then actually, you can find the relations between the pi 2 prime and the pi 3 for the pi 1. So those pi terms are actually dependent on the other pi terms. Of course, pi term has to be independent, right? What that means? Independent to actually within the original pair, original combination. So pi 1, pi 2, pi 3 has to be independent to each other. Let's go back to the resultant result here. So we had a pi 1 here, pi 2. Are they're independent? Yes, they are. Why? The one term has a pressure drop here per unit length. Another term doesn't have it. So we know those are independent to each other. But if I choose like a pi 1 here, pi 1 prime here, is this the independent? Yes, it is independent to pi 2 prime, but not independent to the pi 1 and pi 2 prime. So it is combination of these two pi terms here. All right, what's the point? If you find the two pi terms, which is the number of the pi term you originally calculated from the problem, then those two are independent. If you find another set of pi terms, then those combinations are dependent on another pair of the pi terms. Okay, it's a little confusing, but I just want to make the point. The take-home message is you can choose any repeating variables if you're kind of confused by choosing one. Then you can choose anything. Then you can manipulate it to another set of pi terms, but you have to stick to the number of the pi terms you initially established within the calculation. Okay, so here you always have to find two pi terms. Then there's no third one. Of course, you can find another set of pi terms, but always you should pair two within the analysis. All right, let's take a look at one of the example problems in the textbook. So we have a thin rectangular plate having width, height. So everything describes the phenomena of the flows across the plate here. So we have a drag. It's a function of width, height, viscosity, and density, and the velocity. So it says D is a function of W, H, mu, rho, V. Okay, so what's the next step? Just write down, express all the variables with its unit. So this is a force, which means a fluid mechanical system. So you can use the FLT system, or you can use the MLT system. That's totally fine. So let's just write down all. We have a D, W, H, mu, rho, V. So we went through the conversion of the units. So let's just write down all. So D is MLT minus 2. Of course, this is L. Of course, this is, do we have H here? Yes. L, mu, M, L minus 1, L minus 1, M, L minus 3. Then B is, of course, LT minus 1. If you use the FLT system, of course, you need the dots here. Then you can simply use this is of course the drag force. So F is just a force itself. You can simplify the D as a force. Then rest of them, LT should be all same. But now you can convert the MLT system into the F if you have M inside. So that's going to be FL minus 2T, FL minus, this is F minus 4 T2. Okay, so it's your choice. You can choose one to another. But I'll just go over another example problem that makes you a little bit confused. So let's just solve this. But I'll just stick to the MLT system because we are kind of comfortable to use it. But you'll see the homework problem that you need to use the FLT system. I specified it. All right, what's the K? Number of the variable. 1, 2, 3, 4, 5, 6. 6 minus. What is the number of the reference dimension here? Reference dimension means we have a basic dimensions, 3 basic dimensions, MLT. Reference dimensions, the dimensions you used within the unit system here for all the variables. So we use the MLT, all of them. Therefore, the reference variable is 3. So you have a 3 pi terms. Okay, what do you have? I actually can make one of the dimensionless coefficient here right away from the unit, the set of the variables here, which is W over H or H over W. All right, why is that? Because the units are actually dependent on another one. All right, it's not obvious. I don't know. Yeah, skip that step. We'll just figure it out. All right, what's the next step? Once you find out the number of the pi terms, then what is the next step of the analysis? Repeating variables, which is critical. So you have to choose the repeating variables here. All right, I'm going to choose here. So I need one of the M and L and T. So there's L. Obviously, we have one L, so I'll choose the upper one here. So you need another one for T and M. So T, there's a T here, but with the MLT, another T here, MLT, it's all combination, but here we have a LT, which is simpler. So for the T, I choose this one. All right, for the M, we have a D, mu, rho. So D is the one of the dependent variable we are looking to find the values or the result. So this is dependent variable, which cannot be the one of the repeating variables. And we have a mu and rho. So what are you going to choose here? We already talked about this. Of course, you can choose mu or rho, anything. But here we have a rho is M and L. It's a combination of 2 basic dimension. Mu is a combination of the 3 basic dimensions. So it's going to make your life a little bit easier by choosing rho here. But of course, you can choose mu. That's fine. So we chose W, rho, and V. That's what I did. All right, for the pi 1. The first one, actually, I'm not going to go with the D first. I'm going to go for the H first because it's much simple to solve. So H, W, rho, V. I have exponents A, B, C. It should be dimension. Nope, not there. There. M, 0, L, 0, T, 0. Okay, what do you have here? L, which is L. W, which is L. Rho, ML minus 3. V is LT minus 1. All right, this is very easy one. Okay, we have exponents A, B, C. Can you use the rho here, put any number in B to eliminate the M by other terms? No, there's no other M's, which is a mass within the other unit. So this whole thing should be 0. Otherwise, there's no way we can balance the units. Therefore, B should be 0. How about T? we have L, no M, there's a T. So only T, which is time, is in the unit of V. Then if we have any number in C there, there's no way we can balance it to 0. So C should be 0 too. All right, what else we have? We have one of the dependent variable, H, and one of the repeating variable, L. So A should be -1. Okay, that says pi 1 is just simply H over W. Okay? That's why I just mentioned this right away. Once I just look at the units, you can do it actually after 2 examples later. All right, the second one. Now we use the find the H. So next one is, let's choose, what did I choose? I choose mu here. Mu W rho V. I actually used a different order. Here's my pen here. We have A, B, C. Then it's going to be M, M, L -1, T -1, L, M, L -3, L, T -1 equals T0. We have A, B, C there. Okay, same, let's do it. The easiest one is going to be M, I guess. We have a 1M, 1 plus B there. It's going to be 0, so B is -1. Now T, we have a -1, then there's a -C equals 0, so C is -1. So L, we have a -1 plus A minus 3B minus plus C is 0, so -1, 4 minus 3, so A is 3. Am I correct? I think I'm wrong, some error there. We have a -1 here, A there, minus C there, 3B, and we have C here. It's going to be 2 minus 2, 1, yeah. It's going to be -1. Okay, so it says pi 2 is we have a mu, then all underneath in the fraction, so W rho V. Okay? This is one. Let's use this space. Pi 3. Now for the finally, you can use the drag force, which is D, then W rho V, A, B, C. Unit is going to be MLT 0, 0, 0. Then you can just do the same thing, and you'll just find the pi. The third pi is going to be D square V square rho. Yep. And what if you use the FLT system? Yes, it's going to be same answer. So if either you use the MLT system or FLT system, you should have the same answer, because this is basically you convert the M to F or F to M. So especially this problem, if you look at the reference dimensions here for the all the variables you have, you probably already see that one of the D is just simply we can replace with the F. So basically you can just find the easier way to find those exponents during the calculation. So if you think there's a force related or pressure related problem, or if there is anything like inertial force, gravitational force is applied to the system, you can actually choose the FLT system. So please practice this Buckingham-Pi theorem using the homework problems. You should have one of the problem in the exam to solve the pi terms. And just do not worry about choosing the repeating variables like that. As I told you before, you can choose either rho or mu in this case. If you're just confused which one would be a better one, if you don't have time or you actually don't know it, just pick anything. Then if you have a pair of the pi terms or probably 3 pi terms in the answer, if you just run out of time to manipulate them for the like a Reynolds number, things like that, I don't think it's the big of deal as long as you have a right sets of the pi terms at the end. Okay, so I think that should be the most confusing part in the pi theorem, Buckingham pi theorem here, repeating variables. So please take a look at some hints and the tricks, but again, as long as you don't pick the dependent variables, you don't pick the same dependent units, something like if you choose a W and H at the same time, it's going to be the wrong answer. So otherwise, I think it's pretty much obvious, straightforward up to this point. Just practice with the example and the homework problem. And let's take a look at another example problem. This one gives you the little bit confusing part in the middle of the calculation. So we have a paint here. What's given here is D, diameter, height, depth, and the specific weight, which is rho g, vertical deflection delta, and delta is a function of those all. Here, of course, you can know that here specific weight, diameter, and D is what? Here it says the thickness, all right? Then the E, the capital E is usually called a Young's modulus or modulus of elasticity or just elasticity. So this is basically the property of the material. So determine the functional relation between the vertical deflection delta and independent variables among the dimensional analysis. So basically, you need to find the pi terms. This says delta is a function of d, h, d, small d, and specific weights, and E, Young's modulus. Okay. We're trying to find the delta, so this is dependent variable. So we can just express all in the unit system. You can use FLT system, MLT system. What I used here was FLT system. You'll see why I choose it in the textbook too. This is just L, D, of course L, then A, D. Oh, that's just following the order. H, we have a L again, D, which we have L again. We need a dot. Then we have specific weight, which is FL minus 3. Of course, you can just put the rho G and put the units. You will figure out what you have here. If it is the MLT system, you will see it's ML minus 2, T minus 2. Then the Young's modulus, which is the same as the Pascal, right? So it's going to F L minus 2, which is a Pascal, the Newton divided by the unit area. Then if you convert it into the MLT system, we have had this one before, minus 2 here. Okay, so you'll see why you choose the FLT system here, right? because you'll see the MLT system has one more variables here. But let's talk about the number of the basic dimensions here. We have a basic dimensions that says this is M, L, no, not that one. This one is FLT system. This is MLT system. So we use both 3 basic dimensions. What about the reference dimensions? The reference dimensions are the one we use to express the variables here. All right, what did we use here? F and L. So reference R is going to be just the 2, not 3. All right. Although we have 3 basic dimensions, but we use a 2. All right. How about the MLT system? All right. We have 3 basic dimensions, and we use the 3 all of them. Right. So that says the number of the pi term K is 1, 2, 3, 4, 5, 6. 6 minus 2, 4. 6 minus 3, 3. Do we have 4 pi terms if I use the FLT system? And do we have 3 pi terms if I use the MLT system? Doesn't make sense, right? If you look at the units here more carefully on the MLT system, this is actually same as the one we can divide by the L out of the units, T minus 2, then L minus 1. Okay, it looks like we can have a common combination between these 2 variables. Of course, the other variables have only L here. L, 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 L. There's nothing we can just choose. But here we can have L is, of course, the one of the basic dimension we used, which called the reference dimension. But rest, as M and T, can combine into the one single, actually, system of the unit, set of a unit that can be represented like one new unit, let's say, dimension. Okay, same as the FLT system. If I use the FLT system, F is what? It was the Newton. I don't want to use the same units here. So Newton was a kilogram meter per second square, right? So it means if I using the MLT system, there's M L T minus 2. It's the set of the unit that can represent the F here. Same here. This whole combination MT minus to the minus 2 is actually act as a one single dimension. So you can say the number of the reference dimensions is 3 here. It's actually 2. Therefore, you will have the same 4 pi terms out of the analysis. Okay? Is this common? No, it's not going to be the common in the problem. If it's the problem, I'll just ask you to specifically how many reference dimensions can you find here, something like that. But out of nowhere, if you're given the problem to solve and you need to figure out what the reference dimensions are like this, you probably be directed to use the FLT system to find the answer, right? So that's one of the take-home message today. Then basic dimensions, number of the basic dimensions can be different to the number of the reference dimensions. It can be equal or less than the number of the basic dimensions. It should not be exactly the same number. Of course, this is not that common though. All right, so yeah, I think you need to find this here. Yep. Let's move it here. So here, This is the one you might think before when you're using the Buckingham pi theory. I'm going to pick this up tomorrow really quick, but basically, of course, we have a set of the procedures to find the pi terms. Find the number of the pi terms, find the number of the reference dimensions, and choosing repeating variables, and set up the first pi, second pi, third pi, so on, to find the dimensionless coefficient. Okay, it's all about the same rules. We use the same rule, which is just find the number of the pi terms and make pi terms all dimensionless. And pi terms are all independent. As long as you stick to these three main fundamental concepts, then you can actually find the dimensionless coefficients without any steps like we used before. All right? So first of all, this is exactly the same example problem. This is pressure drop per unit length, and we have defined the problem as a function of a d, diameter, rho, mu, v, which are all the flow characteristics. Then let's find the unit dimensionless coefficient here. All right, number of the pi terms. We have a 1, 2, 3, 4, 5. K is 5 minus R. We have a MLT system before. If I use the FLT, this is actually the FL minus 4T2. It's a typo. All right, now we use a FLT system. So of course, answer should be the same. And we use the F, we use the L, we use the T. There's a nothing pair of the common across the variables, so I can choose all three. So you have a number of the pi term 2. So you'll see the 2 pi terms. For the pi 1, how are you going to find it? All right, easy. First of all, this is my interest, right? Delta P L. It has a unit of FL minus 3. Okay, how can I make things just apply any combination of the operators inside to eliminate the one of the base dimension? Let's say I want to remove the F first here. Okay, simply can divide this delta P by something like a mu or rho, right? There's a 2 option. So I'll just try it. Delta DL divided by rho. The unit's going to be FL minus 3. Then what's the rho here? FL minus 4 T2. What I have here is I can eliminate this F, but now still have a L minus 1 T2. Okay, it's not dimensionless yet. What you're going to do is, okay, I'm going to just find the L and T and see if I can eliminate the one of them. Or I'm going to just eliminate the T first because there's a no T only variable. So I'm going to just remove the T square underneath there. There's a way I can do it by V. So if I have a L rho V square, then I have L minus 1 T square. Then we have the L square T minus 1. I don't think it's a little confusing. Let's just write down all here. L minus 2 T 2. Okay, then I can eliminate these two. So what I have is L minus 1. Okay, still it is not dimensionless. What I'm going to do is just apply D one more, then I can just remove it. So finally, I just try this one. Keep everything else except for the D. Okay, looks like I can eliminate all of them because I have L minus 1, then now I have L. Right, not 0, let's say M FLT 000. Okay, and this is your first pi. And you can try this same step, this method, choosing the mu to eliminate the f first. Then you're gonna just find the one left terms, then you wanna eliminate them using v and d, then you'll see the different expression for the pi 2. Do I have one here? No. All right, so this is the method of the by inspection. You can find the pi terms by inspection as long as you can follow the rule here. So number of the pi terms should be corresponding to the one, the k minus r. Then pi terms should be dimensionless, and pi terms are all independent. That means the one pi term should have a rho, another term should have a mu, so it's not substituted by another term, so there are independents. Of course, it is a pair of the two pi terms. All right, let's just move on to the more dimensionless coefficient tomorrow. Then we can just, I probably think we can, no, not wrap it up yet. Yeah, we'll see. Okay, any questions today? All right, just make sure to download the lab handout again. I had a typo for the reference area of the spheres. Then I don't think you have any issue with the ANSYS, but please just download it from the Soft Center if you don't have it. And just make sure you need a file and a folder at the same place to open it. All right, if you just copy the files only to the desktop or somewhere in the folder, then it's not gonna open. Okay. If you don't have any question, have a great rest of the day. Thank you, guys.